Okay, good morning. Starting a little bit late. Had some what I thought were projector problems, but it turns out my little interface dongle, which is sitting on the table, that splits my USB-C into an interface for the video, my microphone, and a dongle for my wireless mouse, died. It didn't quite make it to the end of my life here. I'm kind of disappointed, but it's got a little flex cable on it, and it gets torqued a lot when you plug it in and then plug about 3 different cables into the other end of it. Because it gets torqued is all I can say, and I've always thought, wow, this is probably the weakest link, and maybe that's what died in it. But now I've got my big docking station with a wideband video and other stuff in it that I've barely used since I bought it. So we'll see how it works. It's not exactly a portable thing though. So a lot of different things that I'm going to want to talk about today. This is, amongst other things, though, my last lecture in my career at UCCS. I don't plan on giving another one unless, I'm going to give a lecture next spring for the high school open house. I'm volunteering to do that, but I met with the dean on Monday because I've been getting a lot of pressure. I have these students that aren't finishing. One just bailed out, just punted his whole defense this week, a couple days ago. Another one is struggling to get finished, but there's going to be some carryovers. So I haven't quit a job really for a very long time. Where I worked at company A and went to B and then went to graduate school, but the dean confirmed to me what I thought was true. December 31st, or as soon as my obligations are done for this semester, I'm absolutely cut free. There's no money that he will pay me in the spring, even if he had it. And he does have it, by the way, because 2 of us faculty are going to be gone. And I thought maybe I could get some of that because I've not been agreeable to the idea of working for free. Everybody has been telling me, do not do that. So there's going to be some disappointments. There are already some disappointments, but he wants me to turn my page and move forward. So my next employer definitely wants me to do that, but it's still hard. So I definitely want nice, neat, and tidy papers turned in because it's a royal pain to grade garbage. Never give me another assignment again that's all crammed together. Some of you have been in the habit of just compressing everything. I can't write notes or do anything on that. It's like being in elementary school or something where you want to write a document and just say it's a neat and tidy thing. I added 1 to 2 and I got 3. Go on to the next problem on the next space. It takes more than that in engineering, and you want to be able to communicate. So at any rate, we'll eventually go over the final exam review sheet, and those of you that just walked in, right over here by the dongle, why don't you come up and just grab it? Grab 2 of them or 3 of them. Yeah, there should be enough. I want everybody to have a sheet so you can write notes on it because it's kind of the study sheet for the final, which will be impromptu. I might add things and delete things, but you can write notes on it about what I talk about. Did you get one for Joe? Yeah, thanks. We're also going to go into chapter 7 of the notes. We're going to cover just a few items on the FFT, or on the discrete time Fourier transform. I've added, over the last few days, I've added a comments hint section on the project, which we can look at. I've refined it even since I first posted it on Sunday night because I found some typos. And then this morning I put up a 1-pager that helps with the bonus problem on the project, which don't be striving for that unless you really feel so inclined. It's kind of an advanced thing. It's not something that we've covered. We haven't discussed digital phase lock loops in this class, which is what the tracking loop for the spread spectrum signal is all about. Or at least that's sort of the control system, signal processing side of it. But I'll maybe glance at that as well. So first off, I want to see, are there any things on this since I don't have anything at my disposal. I added, this is an example I added to the Chapter 6 notes and reposted it. I think I did that on Wednesday or Wednesday afternoon. It's an example. It's in the Jupyter Notebook we've already seen. What I have to do, though, before I even get rolling here, because I had to restart the computer when I was having the interface dongle failure, I need to go back into here and restart Julia so I can get a notebook going. And then I'll have these things at my disposal. Fortunately, a lot of the things that I use, like this interface right here, or what I used to write my notes on when I had to restart my computer moments ago, all that stuff was loaded as soon as I started those apps again, which is helpful to me. So I thought of a couple things after class on the filter structures and what I was doing at the tail end of that, but right now it's not clearly in my head what it was, so I don't want to fumble around. But if you've got any questions on what those homework problems would be, I've got the solutions sitting right here. Does anybody have any questions? They're not due. The set number 7 papers are not due right now, but I do have my solutions. Any questions from anybody? It's a radically different style of homework problem than what you've seen, because it's topology, a little bit more like circuit analysis, and you go forwards and backwards on things. And I'll probably highlight that on the review, because I'll discuss the types of problems that you'd get. Actually, I can discuss all of that stuff then as well. But if there's no questions on 6, I'll move over to get ready to talk about 7. Get that notebook started, and this always takes longer. Load that one up. And this came back right to where it was. When we talk about the FFT, as we move towards that today, I've got three different environments I'm going to show you, primarily Python, because that will be helpful in working the homework problems. But I have Julia up and running. And then, because I never had you do anything with C++ coding, I've got a little example that I built up right here using an FFT and then timing it and interfacing right over to Jupyter Notebook. And I've got that running right here in VS Code. So I'll be able to show you that as well. Meanwhile, back over here, the discrete Fourier transform is the topic of this chapter, and what I do in the chapter of notes is cover material from several chapters out of the book. So it's a combination of things, because it's always been at the end of the semester. It's always kind of a pull things from here and there to get things up and running. But I'm going to stay on the lean side of what I cover out of this. But if you remember back into chapter 2, the second half of that chapter was in the frequency domain. Remember, we had the DTFT, the discrete time Fourier transform. The discrete Fourier transform doesn't have that extra word in there, time. And that's important. The discrete Fourier transform, or DFT, is related to the DTFT, but it's not the same thing. It's very much different, and that's one of the main themes that I want to get across in this part of the lecture today. It's used for similar purposes, but it has a lot more practicality involved with it. So there's different ways to start this discussion. The book takes sort of a longer route where they want to go through a discrete time Fourier series and then relate that to the discrete Fourier transform. my preference has been to cut to the chase, so to speak, quickly and go right to the discrete Fourier transform using this idea here, sampling the Fourier transform. So the first thing that has to happen is you have to consider a finite length sequence. When you're dealing with a discrete time Fourier transform, you're always dealing with a sequence that's finite. See if my battery still works. So the Fourier transform of a sequence, remember, always operated in general from n running from minus infinity to plus infinity. So no matter what the duration of the signal would be, if we're going to take the Fourier transform of a sequence, we're going to look at everything and anything. That's kind of overpowering, right? Minus to plus infinity is like everything. And in a real world system, you'll never do that. And if it's a capture system for getting information about the spectral content of a waveform, you can't do that because that would take forever, right? You just have to be willing to say, I'm going to grab some samples. I'm going to try to decide what I want to do with those samples. And then there's other applications too, time domain filter or frequency domain filtering that I'll mention here. But so the first off assumption is that the sequence is finite. So the way it's always defined in books everywhere is running from 0 up to n minus 1. You could take and grab a signal from anywhere in the discrete time axis and always just say, let's pretend it runs from 0 to n minus 1 for the purposes of calculations. I mean, understand that we have the delay theorem, which will work for the discrete Fourier transform, and it of course works for the discrete time Fourier transform. So that's our sequence. If we take the Fourier transform, and this is just, whenever I say Fourier transform, I'm meaning dt ft. We're going to sum from minus to plus infinity, but because this waveform is of finite duration, we just have to sum from n is equal to 0 up to n minus 1. But the key factor is here the frequency axis is continuous, and that's the problematic part about the Fourier transform. It takes a discrete time sequence and gives us a Fourier transform over all frequencies. Very good thing to have, but if you have to do this on the fly and efficiently, it's not so good because you have to evaluate at some frequencies. And then if you have to go back to the time domain from the frequency domain, that has been our one and only integral all semester. To inverse Fourier transform from a spectrum back to a sequence requires an integration, right? 1 over 2 pi times an integral over a 2 pi interval of x of e to the j omega, e to the plus j omega n d omega. That doesn't sound very practical either in terms of doing it on the fly. So to get into this, we're saying let's consider how we could get x of e to the j omega for a finite sequence, which is this equation here, and then sample it. So that's why the title of this section of the note says sampling at discrete frequency. So pick the discrete frequencies as shown right in here. We're going to let omega k be 2 pi k over n, and k is just going to run from 0 to n minus 1. So it's sampling uniformly spaced from omega equals 0 up to one sample less than 2 pi, because that would be one period. So that makes this these frequency sample values now be omega k, and then notationally we'll just modify that to say it's just a sequence capital X of k, where k is the index into the frequency value. And this is what it looks like pictorially. The W sub n there, which is used right in here, is the notation of what the weighting factors look like. It's sample values of e to the j omega n when omega equals omega k, but it's defined like this. Historically, these are called the twiddle factors. Sounds kind of weird, but that's the name that they're given. And they actually are put into a table, a lookup table, that would be used when you're doing a fast Fourier transform. So the continuous part of the spectrum would be, as shown in the figure, the smooth line, and then the samples are like a stem function. And this one is not included. It's maybe hard to tell, but that's gray. The rest of them are black. So that's just indicating that that's going to start over again, because we know the frequency spectrum is periodic. So we just have n. We have an n-point sequence, and then we have n points in the frequency domain. And if we were to just remember how frequency axis is related to the z-plane, what I have shown on the left there is just how we're taking points around on the unit circle in the z-plane of x of z. And that's just an equivalent. It's showing that the sampling could also be viewed as taking place in the z-domain. And I think the very first homework problem, text problem 8.7, kind of takes that view. It wants you to think in those terms, but you're still taking just discrete values. So you're taking the values like you're doing it around the unit circle. So this is the DFT. If we have an n-point sequence, or if we have a long sequence and just chop out n points out of it and perform this upper blue boxed equation result, that is the n-point discrete Fourier transform. Discrete, emphasized, it's discrete time signal, discrete frequency domain signal as well, because the capital X of k is just at 0 to n minus 1 points. And then you can show, and that's on the next page, that you can inverse discrete Fourier transform, which is like synthesis. The upper one is analysis, analyzing to see what the frequency content is of the n-point signal. And then you can synthesize from the n points of frequency domain data, capital X of k, you can resynthesize the original sequence. What you have to do is add a 1 over n scale factor to normalize things back again. But other than that, this is the relationship. And what is supposed to jump off the page at you is that how wonderful it is to be able to take endpoints in the time domain, map them to endpoints in the frequency domain, and then if you want to go back again, just run a finite sum over that and you're back again. You know, I could use the term from that movie about the mathematician. What was the title of it? A Beautiful Thing. Does anybody remember ever seen that movie? Beautiful Mind, but I'll say it's a beautiful thing. But there was an inventor of this. This was actually invented back in the late 1800s, about 1890 or something. There was a guy named Schuster that was investigating, without the aid of a computer, of course, sunspots and the periodicity of sunspots with over time, I think it was. So he invented or came up with this algorithm for trying to find out harmonic content from a sequence of observations. And then in about 1965, Cooley and Tukey, who are two people that were at, one is at IBM Research Labs. I can't remember if they were both there or they were doing similar research independently, but they discovered the discrete Fourier transform and its fast equivalent, the FFT. And then later, they found out that it had been originally discovered back in the 1800s. So they are, they're credited with sort of a rediscovery of the algorithm with computers available, right? I mean, that changes things a lot. It's a historical thing. I happened to be at the International Signal Processing Conference in San Francisco the year that it had its whatever anniversary that would have been. I don't remember now. So they had a big session on it. It was kind of a big deal. The IEEE Signal Processing Society kind of celebrated the discovery of the DFT and in particular the fast version of it, the FFT. And actually it's a whole family of algorithms that constitute FFTs, but in my mind it's one of the pillars of digital signal processing, the fact that this exists and that this pair exists, that you can go into the frequency domain and go right back out with a similar type of calculation. And the proof that you can come back out again is right here, where you just put in the inner square bracket there, I'm putting in the forward DFT of a sequence, and then I'm right away going to inverse transform it. And in the past we've had proofs like this, like for the DTFT, where we had an integral and we had a sum, and we had to do a little bit of hand waving mathematically to say we can interchange the orders of the integral and the sum as long as we have convergence. In this case, there's no hand waving required because both of those sums are finite. We can just choose to do one sum first or the other sum first. So we can just interchange them, and that's what's done here. And when you do that in this second line, you do this interchange, and you get this sum inside. And if you go through and evaluate what this is doing in terms of the complex exponential there, in place of W sub n, remember that was let's see, right here in the red box, that's what W sub n is. This sum, you can show, and it's written down right here, you can show that when you sum that up, how did I sum that up? This is like going back to the beginning of the course. What is this? Geometric series. That keeps coming back over and over again, but that's how I do that. Finite geometric series, and then you plug in values for m and n, and you see that when m is equal to n, you get n, and when m does not equal to n, you get 0. So that's like a delta function. So that is a delta function sitting in here, and it sifts out only the value of this outer sum now when m happens to stroll by these numbers, when it happens to stroll by n. So it's putting out x of n is what it's doing. Pretty cool, I think. Not that complicated, doesn't require any really super complex math. Geometric series maybe. So that forms the DFT pair, the way of going from a sequence domain, sequence in the time domain to sequence in the frequency domain. And I just comment here, it's sometimes thought of as a discrete Fourier series. One of the things that happens also that is a little bit on the weird side is that if I grab the sequence x of n over n points and now transform it to capital X of k, I will get frequency domain points that lie on 0 to n minus 1, but then I'll also have the exact same points shifted over at another period all the way up and down the axes. So what the book likes to do is use this tilde over the top to say it represents periodic extension. The idea that also in the time domain and in the frequency domain side of the DFT, we have these periodic extensions. So the signal extends, the frequency samples extend. They're not formally present in the time domain side, but for all practical purposes, it's as if I gave it endpoints, and as far as the DFT knows, it was just another same endpoints adjacent by all those multiples of n shifting. Because what the DFT is doing, it's like putting on blinders and saying, I'm only telling it what is on that interval. It thinks that that sequence just repeats up and down the axes. And that's where it gets its connection to the Fourier series, because that's what a Fourier series does, right? You give it one period of a waveform, and you calculate the Fourier coefficients. I don't want to get you tangled up into thinking about it. I'd rather you just think about how it's a sampled version of the DTFT. But needless to say, it is in there. So, and in the frequency domain side, you can put the tilde. And what the book likes to do in both of these cases is they like to say, if you're accessing the sequence, you actually have an add n modulo n, which a shorthand notation they use is double parentheses and a subscript n, meaning that if n runs outside the interval 0 to n minus 1, you're just going to moduloize it to stay in that interval. Another interesting thing you can do, not so big a deal for this class, is you can write this out as a matrix transformation. So you've got a vector little x of n and a column vector big X of n, and then you have a weight matrix W sub n constructed in this fashion, and then you can write that the DFT can be the weight matrix times the column vector in the time domain equals the column vector in the frequency domain. And this happens to be an orthogonal matrix, and it has this property shown down below here. It's not perfectly, its length is not 1, so it's not an identity that I have here at the right end. It's got a gain factor of n, but other than that, it is orthogonal. Rows are orthogonal to other rows in the matrix. Why is this of curious nature is that people that invented fast algorithms for doing the DFT, one of the families is based on this matrix idea, where you can simplify by studying the properties of the orthogonal matrix and how you can simplify the calculations. So I want to go through an example. Suppose we have a sequence that's 1 on the interval 0 to L minus 1. So it looks, oops, got my finger in the wrong spot. And what we're going to do is we're going to eventually zero pad this sequence, because we're going to say it's 0 outside the interval 0 to L minus 1, and we're going to just feed that into the DFT and compare it with the DTFT. So if I just feed it into the DFT directly, it will only capture the 0 to L minus 1 samples, and it gets this sine Lx over sine x function that we've seen before, this alias sinc function. We've seen this before, so that's what the continuous spectra magnitude and phase looks like. If you feed this into the DFT, though, and calculate that out directly for the DFT using n points, you get this expression right here, which is still an alias sinc function, but it has other properties associated with it because it's only a finite duration now. We don't have samples, we only have n frequency domain samples. So if our sequence is, say, L is equal to 10, so we have points that are the black ones there from 0 to 9, and then DFT that using a 10-point DFT, it thinks that the signal we're looking at has got the periodic extension, so it's got the 1s to the left, 1s to the right, and in terms of what the DTFT would view, it would say what? If the signal has the extensions on it, like I've shown with the open circles, what does the signal look like? A constant, B, a rectangular pulse, C, say a sinusoid or triangle, I mean anything else. Which is it? It's a constant, right? It just looks like in the window, observation window, it's a constant over the entire interval. So when it goes ahead and DFTs that, and we sample it at those n points, this is what we get. We get a spike at 0 way over there on the left. And then I'm just showing extending the period, but so 10 is the beginning of the second period, but I get 0 values, and then I've got dashed into there what the true DTFT is. It's got the humps in it, but we're taking our samples in such a fashion that it samples at all the zero crossings of the underlying DTFT. So the DFT is blind in the sense that it cannot see the fact that it was a pulse to begin with, because we just gave it constant values. It couldn't see outside that interval that it was going away, and it does the only thing it can do. It does that. So the point is this bullet right in here. Frequency sampling the Fourier transform with too few points results in loss of spectral detail. In this case, because we set n equal to L, it sees a constant rather than a rectangular pulse. So what we could do now is we can zero pad, and that's a fact that shows up in DFT signal processing. We can go ahead and zero pad a sequence. And zero padding generally means that you're just going to pad the end of the sequence values. We had 10 values to begin with. If we pad to go up to n is equal to 20, we'll just pad it out to 20 total points. And now the DFT is starting to see a little bit more about what the signal looks like to the DTFT. And if we go ahead and compute the spectrum on that, it will now fill in additional samples in between. It will get the samples that you see here. It's still it's still pretty lame looking, right? I say lame because it's like I don't really know what's in between there. So another thing that the DFT has that's kind of bad is it's something called the picket fence effect, where if you walk through your neighborhood like I do with my dog, frequently there's dogs on the other side of fences, so my dog's getting all excited because their dog is going berserk sometimes. But if you're walking along a fence, usually there's just a little bit of gap between the pickets. And have you ever kind of studied how you can actually see into the space, but you're not really seeing everything, right? Because of the pickets in the way. You get a view, but you don't really see the whole thing. Like maybe you get a view and you think, oh, there's no dog there because it's actually hidden behind the pickets. You know the dog's there because the fence is rattling or whatever. You did an experiment back in 2610 with the picket fence effect too for images. I don't know if you remember that assignment. I remember it vividly. It involved the picket fence actually, and loss of resolution meant that you were missing information. So that's kind of what this looks like, right? We're not seeing everything. We have this picket fence going on here. By the way, I'm not a fan of picket fences that are really tight because what happens, they blow down very easily. Steel posts are helpful, but wood posts are not too good. I have a steel fence that has, pickets that far apart, and our puppy was sneaking through there up until maybe a week ago. It was quite crazy because the dog didn't take long to figure out, hey, I can go through this fence. The neighbors or an Amazon driver, when I was on the phone, did pick the dog up one day when I was watching, but I couldn't get out there fast enough. Just curiosity things. So if we increase the picket, we increase up to say 80, so now we start to fill in a lot more, and now we're starting to see that the DFT can be a useful tool to get an idea of what the true spectrum is. It's still frequency sampled, it's not continuous, but we can make it emulate the idea of the DTFT by just zero padding. So zero padding is a tool. It's such a powerful tool at that in Python, for example, you can zero pad very easily, and in MATLAB you can do the same thing. So in this notebook here, I've just done the standard imports. To get access to the DFT, or the FFT as it's called, is the library of things related. The FFT is just a fast and efficient DFT, but to get access to them, to that library which is part of NumPy, you have to go into that sub package with FFT, and as soon as you go into that, and I hit the period and I hit tab so I could just see all of the associated functions that are available in the sub package for NumPy called FFT. And the principal one that I'm going to look at right now is FFT itself. So I'm creating a sequence of 10 ones like we just did. And I'll just go down here to do it down here. And if I go inside of that and hit Shift Tab, you'll see what the options are in the use of the function. I put the sequence in as the first argument, and then optionally, normally it's none, but I can put in a value there, and that value will control how much zero padding. So I can make the sequence longer or shorter. And MATLAB's work the same way. So it says if it is larger, the input is padded. If it is not given, the length matches the length of the sequence. Does anybody remember that from maybe 3205? I don't know if you, because I don't teach that class. Dr. Trimboli maybe would have done that. But at any rate, I'm going to set it at 100 in here, feed in the 10. So I haven't run any of these cells, so I better make sure I run them. Now I'm just going to plot it. And that's just like what I was showing you, right? The exact same thing. If I was to take this number down to 10, you know, it's not, the DFT comes out as exactly 10 points, so I don't see that next period coming along. If I make this 20, it does exactly what we were seeing. I'm also going to just time it with 100 points, so let's get an idea of how long it takes to run the FFT over 100 points. And then if I suppose I decide to run it at 128, I just want you to see, we're going to talk about more about this when we talk about the FFT algorithm, but powers of 2 are more efficient than just any old integer value. So look at what it's taking with 100 values. Now I'm going to go to a power of 2, 128. And it's doing a bunch of averages is what time it does. So it took about the same amount of time. But if I go up really big here to 1023, 40 microseconds, and then go 1024. Notice it's getting faster because it's just that much more efficient. We'll be exploring that more a little bit later. The FFT that's running here under NumPy is called FFTW, fastest FFT in the West, which is one that was developed by some people in Texas. So that's, I guess, why the West is on there. It's like gunslingers and trying to make quick draw or something. I don't know. It's funny though to do that. They have developed that algorithm so whatever number you put into the FFT, whether it be a power of 2 or a power of 4 or some prime number or something like that, they have it try to plug in the fastest algorithm. So it's not just going to resort back to the brute force DFT sum, which is about n squared calculations involved. So it's a very, very powerful thing. Julia uses the exact same algorithm, only you have to import the package FFTW for that. And it does, fundamentally it does the same kind of thing. And I don't know if I'll show you the examples. It turns out not to run as fast when timing it in this environment as it does in Python. I'm not exactly sure why, because it's the same behind the scenes algorithm. At any rate, I thought maybe that would be interesting to you. Let's just take this up to 1024 since I ran it. And plotting it with a stem function is kind of silly because it's very dense. It's very continuous looking right now. So I'd be better off to just say plot. Now it looks really nice. So is that kind of exciting? I mean, what's I'll have to break the news to you is that when you use Freq Z in any of these tool sets we're using, is it computing the DTFT from an infinite sum of values? No, it's using an FFT behind the scenes. It's kind of been keeping you protected by not telling you exactly what it's doing because it wants to be fast and efficient. So back over to here. This is an interesting tour. You can share this with your non-engineering friends sometime when you want to say, what have I learned in my life in electrical engineering? I've learned about Fourier transforms in the continuous time domain. I've learned about Fourier series in the continuous time domain. I've now learned about the discrete time Fourier transform right here. And we didn't cover it specifically, the discrete Fourier series. For a periodic signal, we Fourier transform one period and we get the spectral representation. But we've stopped here at the discrete Fourier transform, DFT, where we take one period, just assume the periodic extensions, or they're implicit, and then we have the points over here and its periodic extension. So this is your anthology of Fourier in signal processing. I think it's impressive. You want to know more? I mean, there's a lot of other things in mathematics that are transform based, but okay, so what are some of the properties of the DFT? Linearity holds, just like it holds for all the other transforms, Z-domain, DTFT, and so on. One of the things that's special, though, it's implicit if you're going to be doing superposition like this, that you have to think about zero padding. I mean, for example, you might decide to pad the shorter sequence up to match the length of the longer sequence, or you could truncate it too if you really wanted to. And that's what the functions I was just showing you in NumPy do. If I was to put in a value less than the length of the sequence, it will just truncate things from the end. So we have that circular sequence shift, time delay in the DTFT. Remember, did change colors. I didn't clear my slides from last year, so this is notes from a year ago. Remember that factor, e to the minus j omega m, if you shift by m samples, pops up, representing just a linear phase that gets applied when we take a sequence and shift it left or right. In the DTFT, or in the DFT domain, because we have this factor w sub n to the mk involved, when we try to multiply by a complex exponential factor in the frequency sample value, the sequence we get back in the time domain ends up being a modulo shifted signal, n minus m modulo n. So what this little proof and discussion does is it starts on the frequency domain side and then comes back to see what that complex exponential is doing back in the time domain. So it is putting in a delay of m samples, but it's what's called circular sequence shift. So if the DFT interval was what I've got shown here, and this is its periodic extended signal, now if we want to shift this signal by 3 samples, what happens is we shift it over to the right by 3 samples, but because of the implicit periodic extensions, you see that this right here is moving in because this is what moved off, effectively wrapped around in a sequence shift, or the way I've got it shown here, it's like a linear with the extensions. So you get that effect. That's why it's called circular sequence shift. And it's clear in the circular sense if you put all the points on a circle, and then if you go from the left side to the right side, it's like clicking the dial and turning it so values roll around and come back in again on the other side, whether you go left or right with the sequence shifting. So that's what this example is. And I have an example in Python here. It's in the Jupyter notebook, so I'd rather show it to you there. It's probably not something that you're thinking you care about, but I guess what I'm going to get to before we finish this discussion is that it happens in some circumstances sort of unknowingly, and it causes what's called time domain aliasing. Remember, when you first learn about sampling theory, you learn about how alias signals will fold down into the fundamental frequency range, right? And I started grading the projects last night, and I'm reviewing and putting points on my solution sheet, and that was an audible thing. You could hear the alias signal. In the case of circular shifting or sequence shifting, operations we're going to talk about here in the next theorem will be that signals will rotate in, and that will be time domain aliasing, which is very annoying. It's not what you want at all. It says the sequence shifts from somewhere else, and generally you want to mitigate that, but it can be a desired operation too. So the example that I have in the notebook over here, well, before I get there, I just did another simple example. This notebook is the one that's posted. It's got, inside the zip package, it's got this Python Jupyter notebook, it's got the Julia Jupyter notebook, and then it's got a folder that's got a C++ project in it that I'm going to show you here eventually. So it's got three things inside of it. So let's just play a little game of, can the DFT go forwards and backwards? So here I'm going to feed it a sequence, 1, 2, 3, 4, 5. FFT that, which is the same as the DFT mathematically. So I run that. So there's the sequence values. This is at 0 frequency. This is at k is equal to 1, 2, 3, and 4. So in theory, if I inverse DFT that, which is the IFFT, I should get the sequence back. And I will. In this case, I get back exactly what I started with, but it's because the DFT, IFFT, or IDFT works with complex values and has to work with complex values. It shows that there's a 0 in here, but if I was to expand these zeros out, we'd find that there's some precision effects in there. So if I know a priori the sequence is going to be real, I can just clean that off by using, oops, I didn't want to, by just using the real operator there at the end. And that's just a NumPy array method. Remember, I don't know if I've shown this to you recently, but oops, my fingers are going all over the keyboard, but not where I want them to go. I did that wrong. Oh, I can't remember how to get it to display all the functions available. There's a lot of types in here, though. There's like D type, which is the data type. Complex 128, for example, is what it is. So if you're, we'll come back to this a little bit when we're looking at the C++ code, but just since I've stopped here, that data type we've been using all semester long whenever we've had complex arrays in NumPy. Complex 128 says 128 bits per complex number, 64 for the real part, 64 for the imaginary part, and that constitutes what precision? Float, double, quad, or something like that. I mean, it's double, right? It's called double precision. 32 bits is single precision float, which is what you worked with in the FM4. 64 is double precision, and that's what MATLAB uses by default, and that's what NumPy uses by default, unless you spec what you want. I mean, I could go inside here, and I could go D type equals And I think I can do it in here. Maybe I have to, no, I have to do it elsewhere. That's a list, so I can't do it at that point. I have to convert it first. But at any rate, I can change it if I wanted to. I'm just going to type this back to real. Then I guess I did another example in here. But down here I do a sequence shift. So I take and form the exponential decay that we were just looking at in the notes, 10 samples long, or a rectangular pulse that's 10 samples long. So there it is. And now I'm going to multiply it by in e to the minus j 2 pi over 16 times k times 12. So I'm going to shift it to the right by 12, and then inverse DFT that sequence. So I'm working in the frequency domain right now, and then I'm going to inverse DFT it. So down here you're seeing what's happened is I've zero padded that out to 16, but as a result of shifting, I've gotten this wraparound effect. So I'm getting the effect of the roll operator, which you explored in problem 1 of project 1. So the n values rolled around to the front side as a result of shifting by 12. Now, to prove that, I could shift by 2, let's say. Then we're seeing we shifted in some zeros from the end, and this one didn't change because I didn't change the math here in the roll. I would have had to change that roll to 2. So now it matches. There's another circular shift example. A couple other theorems. Duality just says that the forward and inverse transform can be swapped around. The only difference being that you have to put an n in there, and then you have to do a negative, you have to consider a negative shift, minus k modulo n. But other than that, the forward transform and the reverse transform are the same operation to within a conjugate, which is what that minus k ends up doing, and the scale factor of n. So if you have a fast DFT, you have a fast inverse DFT automatically without doing much work in it. There are a bunch of symmetry properties. These are the general symmetry properties, the ones that I care about the most, and the ones that factor into homework problems and potentially exam problems involve a real sequence. So when you have a real sequence and you look at what happens to the DFT points, is that they're conjugate symmetric. So if I put in a minus k and conjugate it, it ends up being equal to x of k. So whenever we're looking at the magnitude of a sequence, we have this even symmetry in magnitude and then odd in phase. And I put the dashed line on there because the value at 0 is not actually part of the DFT, it's the next period, but the first point is. So it's just going to be symmetrical like that. 1 matches up with n minus 1 magnitude-wise, 2 matches up with n minus 2, and so on. Really nothing new here because the DTFT was the magnitude was unique on the interval 0 to pi, and then from pi to 2 pi it was just the flipped over, right? And that was the conjugate. So that's the summary here. Magnitudes are even and phases are odd and unique over just the first n over 2 points. Okay, the big interesting thing with the the DFT is, can we use it? We've been talking about it sort of in a spectral analysis sense where you would just get a sampled spectrum. Very powerful, very useful application. But what about, can we do other things with it? I mean, think about the power of the convolution theorem in the Z domain and in the DTFT. Remember, if we could transform a sequence, multiply it by the transform of another sequence, then get it into that product, in this case x3 of k, can we inverse DFT that and get back to the time domain? What's the amazing thing here? We can actually make come true something that you've gotten interested in for many, many years, like starting in 2610, that when you see that convolution can be avoided by just flipping to the frequency domain and then inverse transforming. But what was the hang-up there was you had to go through the inverse transform, which would be an integral. And with the DTFT, the same thing. If we could multiply the transforms together, all well and fine, but we still have to integrate to get back from the frequency to the sequence domain. DFT, though, we have the DFT algorithm. So that's what brings up this idea of circular convolution. We can convolve in the sequence domain, and then we can show that we can inverse transform to get back to the convolved sequence without having to actually do the convolution. But we end up with this shifting, the circular shifting, which makes the convolution be called circular convolution. So this equation down here would be saying if we have two sequences x1 and x2, bearing in mind that they have periodic extensions, and we go ahead and convolve them, we get x3. And then if we were to transform that, we would have capital X3 of k. And what we're saying over here is we wouldn't have to go through this convolution sum to get x3. Instead, we'd transform to get x1 and x2, and then IDFT to get x tilde of 3. This would be so-called transform domain signal processing, where you'd actually do it in the DFT domain and then get back again. This will always work, but if we in particular want to make this operation look like linear convolution, in other words, that this circular convolution, because it involves the periodic extensions, if we want to wring out of that something that looks like linear convolution, then we have a powerful way of doing things in the transform domain. This was the project from a year ago. Remember, I left that on the website. I had this developed in C++, or the students had to develop it in C++, but it was prototyped in Python originally. Just to prove that this is true, I've got the notes down here, though, to show how you would get back to the inverse DFT, and that's, I scribbled on it, just talking about how we would write out the convolution sum on the inside, and then we're looking at going through the inverse DFT of that convolution, and how I just interchanged orders of sums again, and finally get it down to this convolution sum equation. So it's called an endpoint circular convolution. And the book uses another notation. They put a star for convolution, but put a circle around it, meaning it's a circular convolution, and then next to it a subscript n to indicate that it's an endpoint circular convolution. I realize this is the last day of lecture, and you're saying, my brain is busting out all over. You just dropped one new thing in it, and now it's going to explode, right? You've been here before, though. I've been there before, too. So just to prove that it can work, I have a nice little example in here where I'm taking a 4-point circular convolution of two sequences, x1 and x2, I've got the periodic extensions thrown up there because in order to do this convolution sum, which we've got shown right in here, we're going to do it in the time domain and then show that it works in the frequency domain, and then inverse transform it. But to carry this out in the time domain, I have to go after each one of these operations. So I have to take x1 at m and then x2 at 0 minus m if I'm going to go after x3 at 0. So I have to carry that out over 3 points. So what I do to do that is I take the input sequence and just replace n by m, and that's this guy right here. And I think I should delete all this stuff from last year. And then I place the second sequence in the periodic convolution. N is equal to 0 minus m. So what I have to do here is I have to think, what is x2 with minus m in it? So that's flipping the sequence over, remember? So that's going to flip this sequence over. So if this sequence gets flipped over, the dark dots move to the left-hand side, but there's the periodic extensions that are hanging out there. So when it flips around, there's always something filling in the space. So that's what this corresponds to right here. I've just spun it around, and nothing has really changed because I haven't shifted the sequence yet. But then I'm just going to take these 4 points, point-wise, times these 4 points, add them up, and I get 3. You know, I have 2 times 1 plus 1 times 1, which is 3. When I go to x1, the second point, x1 at m is equal to 1, or n is equal to 1, excuse me. So that's this thing right in here. Now I flip it over and shift it by 1. So that's what I'm doing right here. I shift it by 1, which if you compare it to the sequence over on this side, spun around, I shift it by 1 to the right. So what happens when I shift it to the right? This value moves over, and then this value, which was at the end, wraps around and shows up right there. And then I point-wise multiply, get 4, shifted by 3, or shifted by 2, I mean. So here's the 2 case, and then here's finally the 3 case. There's only 4 cases to consider, but those are the 3 points in the convolution, circular convolution sum. 3 at n is equal to 0, 4 at n is equal to 1, 3 at n is equal to 2, and 2 at n is equal to 3. And it's going to be a periodic sequence, so once you have those 4 values, you have it for all the values in the periodic extension, which you don't really care about, but it's just the way the math works. So what about doing this in the frequency domain? I can just show this here by showing that if I IDFT the product of the DFTs, then I can get the circular convolution directly by doing transform domain operations. So x1 of k is just the generic Fourier transform pointwise of that 4-element sequence. And then I'm going to evaluate it at k is equal to 0, 1, 2, and 3. I get those values. I do the same thing for x2, get 4 values. And now I have those 4 values for each of them. And I'm just going to multiply them together, point by point. And then I have to divide by n if I'm going to get set up to do the inverse transform. But just the point-by-point multiplication is these guys right in here. So that's the product of the DFTs, and now I just have to inverse DFT that sequence. And I'm doing that on paper right here, and put the 1 over 4 in there, which is part of the inverse DFT for a 4-point sequence. And then I'm going to inverse DFT that, and I've just plugged in what the weight factors are in the inverse DFT, the W sub n to the kn. So I'm going to run k from 0 up to 3. And then I'm going to evaluate K at, or N I mean, at 0, 1, 2, and 3, and I'll get these specific values, and those are the sequence values, 3, 4, 3, 2, which is what I had here. I know I'm kind of going fast, but no convolution required. None of this kind of tricky stuff here. You just simply DFT and inverse DFT. And I have that exact example right over here. DFT, DFT. I just defined the sequence, and I'm going to DFT x1 pointwise times the DFT of x2, and then I'm going to inverse DFT that product, and then because I know it's got to be real when I convolve two real sequences, and I get that number. What do those values mean? I'm not going to explain that right now, but they are truly the circular convolution. Do they relate to linear convolution? That's the next question. But the cool thing about this is all involving the transforms. And if they can be done fast, this can do filtering fast. So we could have one signal convolved with a filter's impulse response, let's say. Acceptable or maybe not acceptable. We are abstracting, right? We're going to a level of abstraction which says we're just encapsulating the FFT, or the DFT and the IDFT into a function. But I was talking to Dr. Kelker on Monday when I came over to have my meeting with the dean, and he, for once in his lifetime, actually said we have to abstract. I've been saying this for years and years, and that is electrical engineering just continues to spread out. The only way we can survive this spread is we have to abstract our thinking to put things at a higher level and not worry about every last detail unless that becomes your specialty. And I'll pick on Jack right now, since you're interested in coding, right? You've been fascinated with it, so you've said to me, somebody has to understand the math behind what's really going on there, but a practitioner can say, I need this code and I need this decoder. I'm going to trust this library of IP to do the job. Don't we do that in our lives all the time? When things fail, like today, when that device failed, I abstracted the ability of that to do its job for me. It failed, so I got to go in and explore it. If I was a product manager, I might say, if those were sent back to me from customers who had them die, so-called infant mortality. You probably heard that term before, right? That sounds kind of crude, but babies still die. They used to die a lot more often, but that term gets used in engineering, though. Just say a product doesn't really meet its lifetime expectation. They'd probably bring that back into the factory, tear it apart, and see what failed on it so they can understand how to make it better. Does that make sense? Now, that's not true of everything in our lives. My wife and I buy new appliances. You go to the store, spend a lot of money for a washing machine and dryer, and you ask the salesman about how long can we expect this to last. Oh, just a few years. You know, we had a washer and dryer when we got married that lasted about 25 years. But now they say they won't last more than 10 years. And if you're not shopping for those items yet, wait till you do that. You'll spend a lot of money, and then they'll tell you it's not going to last. Has anybody heard that story before? They haven't made out of recyclable materials, though, like a dishwasher. We've had that replaced, I think, 4 times. Stainless steel, beautiful on the inside. It goes back to the factory. They recover all the metals from it. So at least, you know, the metals are being recycled. The circuit boards, I guess, are recycled too, because that's what's died on ours. The brains, the electrical engineering part of it, frequently is what goes out. I got sidetracked on that only because I was talking about abstraction, right? But I think that is part of our lives. It's the only way we can manage complexity with our technology, that I think. I love drilling into stuff, and all of you should love drilling into stuff if that's your specialty. So now I'm going to talk briefly about circular convolution, linear convolution implemented. So when we do circular convolution and want to compare it to linear convolution, we have this as our starting point. This is linear convolution. Back in chapter 2, we convolve two sequences together. We flip one over, slide it past. And this was a homework problem in the book. If you have an L-point sequence convolved with a P-point sequence, the convolution is at most L plus P minus 1 points long. Remember that somewhere in your life? Another way of remembering this is when you do a general convolution, the start of the convolution is at the sum of the two sequence starting values, and the end is at the sum of the two starting values minus 1. So if I had L minus 1, which was the end, and P minus 1, which is the end, I would add those together. Nah, I said that wrong. It is the sum of the two ending values. So the first one ends at L minus 1, the second one ends at P minus 1. Add those two together, and you have L plus P minus 2. There's a total of L plus P minus 1 points in it, though, right? Because we have the 0th point. So now if you do circular convolution, we have this thorn that comes about because of going into the transform domain and coming back out. We have that modulo property. So how do we deal with that? Oops. This is a messy drawing. I'm just going to try to erase my notes on here. This is trying to depict the idea that the clear boxes are the sliding of the x2 signal times the x1 when you do the convolution sum. And I've just simply put in the shaded boxes the periodic extension. So as you bring this signal by, and it's going to hit this window that runs from 0 to n minus 1. As it's engaging it and then sliding by, you're going to get this clutter. I'll call it clutter from the nearest neighbors there. What appears to be the nearest neighbors are those two green X's. But actually, you only have to worry about that neighbor that I left in there, because that one is present when you first start engaging. In other words, when this point right here first lands right there at 0, you've got part of that shaded with the X through it box interfering when you do the multiplying pointwise of sequences. And then as you eventually drive all the way through, let's see, switch to blue, if it will let me do that. Oops, I didn't quite get that right. You eventually drive it all the way through, keep pushing it to the right. The gray box will be all out of the way, but it will have impacted some of the early on convolution sum, circular convolution sum outputs. So another way of writing that out, and I'm going to skip the math there and just say I can decompose it into the convolution of those periodic extensions with the one signal that we didn't shift, and we'll get these things I was calling the clutter coming into play. And these are the nearest neighbors. The desired is the one in the middle, and then we have the r is equal to -1 and the r is equal to +2. Those are the nearest neighbors, but this one is not a problem. That one is a problem. So we would like to have it free of the clutter or time domain aliasing. So the only way to do that is to zero pad. So what we have to do is make the space around the two sequences padded so that we don't have any effects of wraparound. So this is the bottom line summary. It says 0 pad, the sequence is out. So we have to choose a transform here that's greater than or equal to L plus P minus 1. So we just 0 pad the sequence of length L up to N and of length P also up to N. And as long as that N is greater than or equal to L plus P minus 1, this is like a knowledge thing for the last homeworks and presumably an exam question. You just pad it up. So the 0 padding is shown in here. And this way, when we take into account the clutter term, we don't have any interference getting thrown up from that clutter term. So we have no time domain aliasing in the end, and it has to do with the fact, as I'm showing in here, I've padded that sequence, so when I spin it around and slide it through, it's it's got zeros in there, so those won't add in the time domain aliasing. So we get a clear shot down here. And this is all because we were interested in exploring the ability to make circular convolution emulate linear convolution. Just remember, that's what this is all about. Can we do things in the transform domain? We don't want to ever do that circular convolution that I stepped through a few moments ago, where you have to tediously shift and take into account periodic extensions and do a convolution sum type operation. We want to go to the frequency domain, come back again. And if you're doing enough points, it's more efficient to do the forward transform and inverse transform. It doesn't sound right that you could actually be more efficient, but if the numbers are large enough, you can actually get traction on this. And in particular, you can have the filter be pre-transformed to the frequency domain, or it can be adjustable. It can be an adaptive notch filter that can be notching out interferers out there, and you just adapt its coefficients to your environment and then send your signal through in the transform domain to remove interference. Adaptive interference cancellation is what it would be in combination with frequency domain filtering. Does that sound plausible? Transform domain signal processing has been around for a long time. So I have some examples of that here in the notes, but I think it's better for me to just show an example down here. The examples are taken from the notes right here. So this is the example. Example 7.4 is here. It's done in Python, but I want to make it live, so I just want to show you what's going on with this. So here, my sequences are of length, let's see, let's go to the example and make sure I know what they are, 10 and 14. So I've got two different length sequences. One starts at 0 and then stops at 9, and the other one starts at 6 and stops at 13. So it actually has 14 total points in it, but it's padded with zeros up front. So even to operate on this, we have to get a common basis. But in terms of this theorem, though, we're going to be heading for the idea that we have to use a DFT that will be of length 10 plus 14 minus 1, which will be 23, right? We're going to see that over here in a second. It's talked about here in the notes, but we're going to start by trying 16, be kind of naive about this, saying that, well, we never go, 16 is right out over here. Why don't I just use that? Because it encompasses both signals with my DFT, and then inverse DFT it. What does that do? So I'll do that, and I have this plotted up here. So here's the linear convolution of the two rectangles. We know if we convolve two rectangles, we get, in general, a trapezoid, right? A triangle, if they're equal length and differing lengths, you get this trapezoid. So there's a trapezoid. It runs from 6 up to 22, I guess, is where its non-zero points are. And we could get that by adding the starting and the ending values together from the definition. That looks cool. We're running with just 16 points in our DFT, IDFT, and the math is all, it's written down, let's see. I'm having a hard time laying my eyes on it. It's right in here though. I'm doing a linear filter, and then, yeah, here's this one line does the whole thing. It forward transforms, multiplies, and then inverse transforms and takes the real part, all in one line of code. But what we're seeing is we're getting some of the wraparound effects because of only using a 16-point transform. We get regions above 15 that are wrapping around to 0. That's that aliasing, that garbage clutter term. But then it rises up, and it falls down, but it doesn't go back to 0 because, again, there's more clutter in that. There's actually the next periodic extension of the signals that's actually in there. So look carefully at what's going on. This for sure has to go away, and this has to go all the way down to 0. So let's just increase this to 20. So I'm moving it by 4. And basically you're seeing now the aliasing is still there, but it doesn't start at such a high level, and it's actually getting down to 0 for a few samples. But this is still undesirable because I've got that clutter in there. That's not part of the linear convolution. This is going down to 0 on this side, but I still have some remnant in there. So if I go to 22, oops, almost there, right? I've still got one little point sitting in there that is not present in the linear convolution. So I take this up to 23, and I'm good. The green is just simply the periodic extension, you know, the repetition coming back through again. If I was doing this with a power of 2 FFT, what would I have to do? I'd probably have to go, or I would have to go to the next higher power of 2, which would be what? 32, right? So I do that. And now it's looking good.
Is there a laptop charger right
Yeah, there is.
Thank you very much. Sorry about
How many hours ago did you leave it in here?
that. Last morning,
Okay.
9:25 class.
So does that make sense? I only asked him that because I've gone back, and most of the time I find my stuff, but I have gone back and not found my stuff. So I've lost stuff that way. Looks good, doesn't it? We would not ever be dealing with this. This is just what we get out of our IDFT, though, and it's faithful, and it's the next higher power of 2, which is another type of homework question and another type of question for an exam. I would say, suppose you want to do a linear convolution of 2 sequences using the DFT, IDFT. You've got a 0 pad using that L plus P minus 1 formula, but then if you want to do it using an efficient power of 2 transform, you'd have to take it up to the next higher power of 2, just like I did here. It would be going from 23 to 32. If your formula said 61, you'd have to go to 64. If it was 33, let's say, that we got for our length, what would you have to do to be a power of 2 to make sure no aliasing, time domain aliasing happens? 64, right? So it's like swallowing hard, saying I have to bite the bullet on this one, but there might be some positive thing that could come out of that. You might decide to build a higher order filter because you've got to have more samples in the impulse response. So the notes walk through that pretty well. What if we have to filter a sequence of possibly infinite duration? So now we want to do this circular convolution using DFT, IDFT, but one sequence is infinite duration and the other one is an FIR filter. So we can do that. we can take our input signal and break it up into segments as a superposition of shifted subsequences. And then if our impulse response is finite, we just call that P. And then we have subsequences of the input, which we've broken down. And we break those down. And I think, yeah, I've got the picture in here. So you would chunk this up like this. And then you would take this, circularly convolve with DFT, IDFT, this chunk, then do it for here, here, and here, and then paste them back together again. So what you have to do is you have to put zero padding in, because when this H convolves with this subsequence, what's it going to do? It's going to spread beyond the boundaries, because convolution always spreads things out. So you'll end up with something like this, where it will stretch longer, but you've got some zero padding in there, and that's what this is showing. And then when you sum them together, everything's nice and fine in terms of being a continuous with no time domain aliasing showing up in there. This is breaking it up into non-overlapping sections, putting the zero padding in. So now when you convolve with each subsequence, you get some tail-off effects, but those are added onto the next sequence, so you have a small amount of overlap, and you can put it together, and it looks beautiful. Again, I'm excited about it because I've had to do this before. If this is the end of your life in DSP, you're probably not nearly as excited as I am, but it's still cool to know that you can do things like this. It's just keeping pushing on and exploring. So the last thing is to go through briefly the discrete Fourier transform. I just want to show you some things that are simply amazing, and stare at it and say, who would have thought of that, or how did somebody think of that? Because it's like through a bunch of stuff, we'll see somebody said, let's do this trick here and here, and then they extended it, and then pretty soon they developed a radix 2 FFT algorithm, and it's very powerful. So we're going to take a break. I'm going to ask you to be back in 10 minutes if you can make that work. So I'm going to pause. Okay. We're back from break. It's going to be a mad dash, a crazy fast dash to get through stuff. So I'm going to be pulling the plug here and there and saying a few things. But I want to get through this and maybe a couple simple concepts after this. So computation of the discrete Fourier transform. This is what makes the DFT morph into the FFT, and notice that I'm saying algorithms, not algorithm. There's not one FFT. FFTW is a collection of algorithms that has been compiled into an efficient C++ library that people can tap into, and it's just this abstraction idea again, right? You plug in, I want an endpoint FFT. Actually, it's a DFT, but I'm calling it an FFT because it's a fast version of it. But what it does behind the scenes, you're abstracted from. You just know, or I suspect, that powers of 2, powers of 4, and things like that are going to be faster than non-powers of 2, or non-prime numbers, let's say, 2. So we have, this is our direct evaluation, and back in the olden days, people looked at what is the complexity, so they're always looking in terms of complex multiplies. So to do a single point, each point, for each value of k, I have to do n complex multiplies in general, because there's a product in here, and n minus 1 complex additions. Why n minus 1? Because if I have n numbers to add up, I first add first number with a second, and then I keep adding, and that adds up to being 1 less, so it's n minus 1. To do all the points, I have to go through that n times, so n becomes n squared to do the entire transform, and n times that is the number of additions. On top of that, though, is the complexity that in hardware, to do a complex multiply requires 4 real multiplies and 2 real adds. So start thinking about going to the gym and lifting weights, doing pull-ups, push-ups, whatever you're doing. You're doing a lot of lifting constantly whenever you have to do these sorts of operations. So I'm only going to keep track of complex multiplies, but you can map it out again to this operation right here. And if you're working in the FM4 like you did this semester, you can write a class or write a function that will do a complex multiply, and you're going to have to do this type of thing. It's not built into that library unless you use the ARM CM/sys DSP library. And by the way, I was looking at stuff last night because I'm trying to debrief some people on stuff. I found out that CMSys DSP is now on a GitHub site. It's readily available. They talk about how to build it for different platforms. And the people at ARM actually wrote a Python implementation of CMSys DSP that tries to emulate everything that's in the current CMSys DSP so that you can run it, prototype things in Python, and have it be bit true right in Python, which it uses NumPy, of course, but I thought that was interesting. So that's available too. You can pip install it, actually. I just made that discovery last night when I was looking at something else, because ARM sent me an email saying there's new versions of their tools out there. So the biggest class of algorithm, the one that was closely related to the one that was first discovered by Cooley and Tukey, is the decimation in time radix 2 algorithm. I think Cooley and Tukey invented the decimation in frequency. We'll see what that is right after we go through the decimation in time. It was just a matter of thinking and how they viewed it, but it's radix 2 decimation in time is what we're looking at. Because it's radix 2, that means we have to choose n a power of 2. So we're always talking about this value nu that you're going to, it's how many stages you're going to have in your algorithm. So 2 to that number of stages is going to be the number of points. And the smallest transform that's done is always a 2-point transform when you decompose with a radix 2. So the first thing that you can do with a radix 2 development is you can take the DFT calculation and just break it up into even and odd points. So you take x of n and index over the even values of n, 0, 2, 4, 6, 8, and so on, and then over the odd values. Why did Cooley and Tukey do this? Why did Schuster do any of this back in the late 1800s when he was only working by hand? He might have actually done this because even though he didn't have a computer, he was going to do hand calculations and wanted to find a faster way to do something that he thought he could make faster. Does anybody find that interesting? If you like history, this is like what makes people think of trying to do things. And all of you will make some discovery, or I've already made a discovery of something that you feel like was an innovation. Maybe it's already been done before, but you didn't know it, it wasn't pointed out in the book, and you just come to this realization, hey, I can make this faster. So they decided to break it up into even and odd, and then the logical thing to do now is to re-index these sums, so they're going to run over the odd points, so it's going to be an n over 2-point transform over the even points and an n over 2-point transform over the odd points. So far, everything looks pretty lame. It's just like we decided to break it up into 2 pieces. What do we do with it now? What's going to save computations? Because right now, nothing has happened to morph this into a computational savings. What happens next is where the amazing thing begins. Re-indexing, they notice right in here that we can factor out w sub n to the k, and so they do that. Again, not particularly exciting. We still have the twiddle factor basis is still n total points, even though we've got it broken down into two n over 2 point transforms. But then this realization, not simply amazing anymore, but I think it was interesting at the time, was that what is w sub n to the 2, pulling the rk out in front? So w sub n to the 2 is just, here's the definition of w sub n, but now there's always this 2 up in the numerator. So they take that 2 and jam it down into the denominator, and you've taken n, which is a power of 2, and now divided it by 2. Still maybe doesn't seem very exciting, but this is the innovation. So now what we've got is two n over 2 point transforms that are using inside of them the basis set that is just n over 2 points long. In other words, sampling around the unit circle e to the j omega at n over 2 points. So these n over 2 point transforms run, and the second one has to have this w sub n to the k. That's the only place w sub n, as opposed to w sub n over 2, shows up in the transform. So in general, this is, for an 8-point transform, what has gone on. We've got an n over 2 point on the even points and n over 2 point on the odd points. But then when the odd points get merged in to form the total of 8 points, there's the combining weight factor, all the way up through here, that brought in from the math on the previous page. And I call this last stage, by the way, is called combining algebra, the algebra that brings the two n over 2 point transforms into an n point transform. So this is a stage of so-called combining algebra where you're just, and I'm using a signal flow graph representation right now. So you do have n complex multiplies thrown in at the end, but you have two n over 2 point transforms. So now if you take the burden of that and tally it up, we've got two n over 2 point transforms, so that's 2 times n over 2 squared. And then the DFT combining takes n points of n complex multiplies. So that's what we have for complex multiplies under this decimation, so-called decimation by 2 into even and odds. Then the adds, similar. So in terms of multiplies, if you multiply these guys out, you get n plus n squared over 2 are required. You're probably saying, that's interesting, but it's not all that great. But look, we don't have n squared. There's at most n squared over 2, which is a savings right there. It's not huge savings. Like if we had a 4-point transform, we'd have 16 over 2, which is 8, versus 16. Plus we have another 4 that would be in here, so that's 12. But it's something, and that's, somebody had to have the courage to say, let me take this another step. So they now break down the n over 2 points into n over 4 points, repeat the whole operation. So now an n over 2 point is now 2 n over 4 points. There's another combining algebra associated with that. And if you take it down for an 8-point transform, you can decimate it down twice. So you're going to go from the full 8-point transform to a 4-point, and then the smallest decomposition will be the 2-point so-called radix 2 butterfly is what that's called. It's called a butterfly because it looks a little bit like a butterfly in an abstract way. It's like wings that are above it, and everybody see that? That's what it's called, a butterfly calculation. And then this combining algebra is to take the n over 2-point transforms on top and bottom into make the n over 4-point equivalents, and now the combining algebra just gets applied to that to make it the 8-point. So you just combine it. It all looks the same though, and if you look at it carefully, you can see that there are fundamentally, the computation unit is always the same, right? No matter where you are in this flow diagram, the smallest computational unit is the radix 2 transform. And another property that it has is it's called an in-place computation. You have 2 points coming into this butterfly. You can have a temporary storage, but then you compute 2 new values and you just put those back over the original values once you used a bit of temporary storage and then can restore them. That's another big thing when you go up to big sizes. Storage was an issue in the very beginning for sure, so it has that feature as well. So after you do this, those 8 times, you end up with, if you look at this flow diagram, we've taken an 8-point transform, and log base 2 of 8 is 3, so we have 3 of these stages. And each one of these stages has n complex multiplies, or actually 2n complex, no, it has n complex multiplies. So after we have these stages, or new stages, and the number of complex multiplies and additions, each is on the order of n log base 2 of n, since that's what the number of multiplies and additions are. So we have an n-point transform, we decompose it into log base 2n stages. So what we're looking at now is that versus n squared. So if we're going to do 2 to the 10th, a 1024-point transform, direct evaluation is n squared, which will be 2 to the 20th, a million complex multiplies. With the radix 2, we're down to just 10,000. It's pretty powerful, right? It's like in 1965, computers weren't as fast as they are now. This was just phenomenal, 2 orders of magnitude. And you can go a little bit further. Each butterfly had 2 complex multiplies in it, but because this relationship between them makes this property holds true. It's just a minus sign that's different. So you can back this complex multiply out, and you can do it once and then just do a sign change. So that makes this number. And this is kind of your reference number for radix 2 that I want you to make sure you know about when you take the final, which will be open book, open notes, but you still may want to write a crib sheet. This is number of computations is on the order for either adds or multiplies of n over 2 log base 2n. I already said it's in place. Talk about that. The only really bad thing about this is you've got something called bit reversing. So if we go back and look at this, you see that they come out in the normal order, 0 through 7, but they have to go in as 0, 0, 4, 2, 6, 1, 5, etc. So that's called bit reversing. Bit reversing just means that you take the binary representation of the index and you have to flip the order of the bits. So first point is fine. X4 is actually just the reverse of 0, 0, 1. So this chart depicts that idea of the bit reversing. And this is just a chart now with the n over 2 factor showing you what the speed up factors are for different sizes of transforms. And then here's a listing of a C version for the FFT. And this is not FFTW. This is not particularly efficient, but it's easy, and I've recoded it into C++, made a class out of it, just because I like to have something I can lay my hands on when I'm prototyping stuff. Like in my work that I was doing at Augustus, I just put this in to use it, so I didn't have to put a library in of FFTW or something like that. Decimation in frequency follows immediately from decimation in time. I write about it in here, but what happens when you get all the way done with this, this is the decimation in frequency. They're identical to within the flow graph transposition. Remember the idea of a transposition? You can transpose a network, run it backwards, flip the arrows and everything. So this is just the flipped version of the decimation in time. And it has the inputs in normal order and the outputs are in the bit reversed order, but the computational count is identical. So it's decimation in time, decimation in frequency. I'm pretty sure Cooley and Tukey discovered this, or rediscovered it. I don't remember about Schuster, what he did. And the only reason why I know about Schuster is because I was at that conference that summer in San Francisco when they had a special big deal about the anniversary, I guess it was maybe the 100th anniversary of the FFT. So I learned history at that time. I didn't go back and read the papers though, I found it amazing. A lot of different applications of FFTs. We really don't have much time to spend on it, but I'm just going to briefly show you what you can do even if you're coding in C and how fast that is. So I wrote a notebook here, and this is now in VS Code, but I wrote this notebook to just generate a test vector. So I'm generating a 256-point test vector of cosines. I then have a handy little function that I wrote in Python that stores it as a binary file, which I call a DAT file, as in data. And because the FFT works with complex numbers, I just added complex numbers to it because I know my decimation in time algorithm is going to replace the input values with the transformed values. So I need to make sure my array is complex. I check it out right here and see it has indeed, it's got zeros in the imaginary parts, but it's now pushed in as a binary file. And you can see in my directory tree for my project called FFT CPP, I've got a file in there, FFT test in. I've got this notebook, and I just did a plot. I just transformed it right here on the fly with this line using NumPy, but I'm going to return a binary file, which is going to be the FFT of that, and I've plotted the spectrum of that just to prove that. What do I do in the C code? If you're interested, at all interested in putting this on a Windows machine, you can remember I have this that explains this I did for last year that talks about setting up msys on your computer for C++ development using MinGW and the msys2 libraries for the tools. So I have that set up on my Windows machine here. It's in a folder, and then I have paths set. That document I just referred you to explains how to do everything. I use makefiles, which is something that comes from the Linux world. A makefile is just a script that tells it what I want to do, how I want to build things. If I had a multi-file project, I'm just showing you this because a flag that I set, I'm running C++ 17, I want to put in my build ggdb, which is the debugger for C++, but then I added another line on there, -03. Those of you that have been taking the lab, what does that mean to you?
Optimization level 3.
Yeah. So if I turn that optimization off and do my build and run it, it's pretty disgustingly slow, but if I put that -03 in there, it runs pretty fast. So here's my main module. I'm incorporating a bunch of includes from the standard C++ library. In particular, I'm using vector and complex. And then I'm also using my library on the C++ side to read and write binary files. That's a header file that goes with the C code over here. And then I've also got my FFT library, which has a header, which is an object-oriented FFT. So if I was to just double-click on this, it's just defining the FFT that we had. I showed you in the notes, but I wrote it up as a class. So now you can instantiate an instance of the FFT object, and then you can either run a method that's FFT or a method that's IFFT. And this builds a table on the fly, so it's very inefficient. It doesn't have a lookup table like it should. At any rate, I'm going to go, in this case, I'm doing a 512-point FFT. I thought it was 256. I guess I'm zero padding, so I'm running with zero padding right now from 256 to 512, which I didn't even remember that's what I did. Can open up my terminal window down here. Okay, so I just wanted to switch to the folder, and now I can do a make if I want to. It says nothing to be done because I haven't edited anything in it, but I can run my code. And it's in a bin folder over here. That's where my executable goes. And it's just telling me it's taking 5 microseconds to run this. And I think I was getting around 4 microseconds in Python, but that was for 256 points. So here I'm running 512, and I'm running 5 microseconds. So the C++ is a little bit faster. If I was to rebuild my code without the optimization, it would be a lot slower. I'm not going to take the time to do that, but I do want to emphasize that with good C++ coding, you can build objects and you can abstract, just like we were talking about, a lot of the processing. I read in an array. It goes into a complex vector that I've created a name for, complex 64T. It's a data type like you've seen in the FM4. And then I'm using something from the Chrono library of C++ to allow me to do timing. So I have that set up here. I create, actually my NFFT is 256, never mind, because I redefined it right here. I redefined it to be the size of my input array, which this is, just telling me that I've got a bunch of methods that go along with the vector type in C++. Then I create an instance of an FFT object, FFT1, make its length be 256, and then I'm going to use a method on that object called FFT, and I'm going to give it the calculation. It does an in-place calculation, so xin is going to come back out of this function call or method call as the transformed variable. I wrap timing around it, store the difference of the time, and then I write back out as a complex binary complex file xin, which is actually the transform, and the rest of this is just the timing. So the DSP is really just in a couple lines of code. I mean, don't be super fearful of C++. You do have to learn the language and particulars about it. It's not a trivial language to learn, but you may see that in your future too. But over here, all I did was read it back in, and then I just plotted it down here as the transform. This is my way of working in C++. I create test vectors, and then I leverage Python or Julia to do things like this to instrument my C++ code, because C++ by itself doesn't have a graphics library unless you were to integrate that. So I just leave it bare like that and read and write files, and it's not too bad. It's actually pretty nice, I think. And I use VS Code. VS Code has its debugger that works wonderful on C++, so it's all really nice tools that we have. Never had any of this stuff when I was a youngster. I had to work on a mainframe when I started, and I sat, used punch cards, but then we eventually had terminals, but you didn't have anything you could carry around, and you didn't even have remote login, so it's changed a lot. So an application that I want to just briefly talk about, we've already talked about transform domain filtering. You can make that look more compact in what's called overlap and save and overlap and add. This is kind of what we were talking about when we said we would transform an infinitely long sequence. So here we've got an infinitely long sequence. We're going to transform with zero padding segments of the input, and then we're going to transform, usually in advance, the filter's frequency response. And then this method is called overlap and save. So we have to discard some of the overlap points, and we just save endpoints when we do a 2 endpoint transform. So n new points get brought in, and n transform points come out. Another way of doing that is called overlap and add, which is just a slightly different configuration. The textbook talks about this as well. This was the essence of the project from last year, where I had them use C++ to do an overlap and add algorithm and time it and just see if it was faster than in Python. I had you guys, remember what I had you do that was special? I had you try out the polyphase decimator from Julia, which it ran a lot faster, right? Amazingly faster. So, I mean, these are things to be on the lookout for in your career if you're going to be doing this kind of stuff. So I do have overlap and save and overlap and add built into my library of Python code. This should come as no surprise. I have this built in, and the methods are OA filter and OS filter. So I did this when I wrote my dummies book. I never thought anybody that bought the dummies book would ever try this out, but I wrote it because I wanted to have it to be available to play with in this class. So here I take an example. I'm just going to run one case. I'm going to take a 60-point cosine sequence, and I'm going to do transform domain filtering with a, what kind of filter is that? You should know. If that's the impulse response, 1's divided by 5. It should stick in your brain. It happened back in chapter 2. Pardon me? Yeah, it's a moving average. It's a 5-sample moving average. Remember that? It's a causal version of the 5-sample moving average. So I'll run, and I'm now going to break my segments up into 20 points each, and I turn on this option true so that I'm going to get a matrix of the subsequences and the filtering of the subsequences. So I run that. This is the result of doing that. So it looks like a sine wave went into a filter and has a little bit of a transient at the beginning, and then it gets into steady state. The full matrix that comes out, which I wrote into the code only for a moment like this to show you how I'm using overlap and save, I can plot it down here. And these are all the subsequences of 20 points that are being calculated along the way. And then remember, like we talked about before break, this is overlap and add, I guess. What am I running? Yeah, overlap and add. So overlap and add has some overlap, and they add up. So these overlap points, this just shows you how it's overlapping and adding. And then down here, I just simply sum the columns of that matrix and plot it. And lo and behold, it is, the output that I plotted before. That just is demonstrating how the mechanism of the overlap and add works. And overlap and save is just a little bit different. And this is how an example of how the overlap and save was written. This was part of the project from 2021, so I had that in this notebook. Cool or not cool? Probably not cool, right? You're not super excited about it, but you know, I implemented some of these things, and in C++ is what I've done more recently. Here in this example, I guess I did a more sophisticated filter. I used a higher order FIR filter, and I just show the end results. I don't show all the stuff in between. Last thing I want to talk about, this will be really fast, is can we build a spectrum analyzer using a DFT, obviously implemented with an FFT. So this is the block diagram. We have an analog signal. We're going to sample it with our C to D. We're going to probably want to window it, so we just don't have rectangular values. We're going to window it with a tapered window and then take the DFT. So the math is talked about in here. There's some optional homework problems to get into this a little bit, but this is one of the fundamental properties of the digital spectrum analyzer. Omega would be our radians per second values. So if we're going to do an endpoint transform, the resolution we're going to get in the discrete time domain is going to be 2 pi over nt, but what really matters to us is this. These two equations right here are kind of the crux of the matter. If we build a digital spectrum analyzer like this block diagram shows, and our sampling rate is 1 over t, what is the nature of the spectral estimate we get, or the VK we get out over here, relative to analog quantities? Delta F, the spacing between the frequencies, is just going to be Fs over n, the sampling rate over n, and each individual point in the transform domain has got an index k, but back in the analog domain it would correspond to some analog frequency, k times Fs over n. This is like a simple back of the envelope calculation. If we're going to digitally analyze a capture at such and such sampling rate, and you want to know what the resolution is, the frequency spacing, it's just Fs over n. And if you want to know what index of the DFT or FFT, what frequency in the analog domain it corresponds to, it's this. So the type of problem that I can make out of this, which I think is fair, is to just simply say, I want to build a spectrum analyzer, here's my sampling rate, or I can put in the problem, what sampling rate do you need? If the bandwidth of the signal is, say, 10 megahertz, I should sample at greater than twice that, right? And then suppose I want to get a resolution of 1 hertz in my spectrum analysis. What would you do? You would go to this bottom equation and say delta F needs to be 1 hertz. Let me just write that down here. And I said Fs is 10 megahertz. So I just spin that around and I say n has to be greater than or equal to Fs over delta F. And if I was at 10 megahertz, that'd be 10 times 10 to the 6, so that would be check my math, am I doing this right? 10 to the 7. Okay, you following me so far? So now I know what my number of FFT points needs to be, and now I can just go over to Python. So I can calculate something here. So I have that, and n has to be equal to Fs over delta F. So I can go up here and say delta F. oops, I need to put N in here. Okay, that's a pretty big number. That's going to be a large size FFT. 10 million point FFT, what that is. Pretty good size number. So maybe I only wanted 10 hertz resolution on a 10 megahertz signal. So that's a little bit smaller. But now what you have to consider, log 2 of n is 19.93. So if I have to get that, I want an FFT size of 1 million. Is that what I got here? Yeah, 1 times 10 to the 6th. That's not a power of 2. So this log base 2 of that says I need, I'd have to raise 19.93 up to 20. So I'd have to go with 2 to the 20, which would be an FFT length of 1,048,576. So that can be another part of the problem, to say you're going to have to go with the radix 2, so you have to raise the power up to the next higher power to make sure your resolution is at least whatever I was asking for. In this case, I changed it to 10 hertz. So if you do this design, you'll be tighter than 10 hertz. If I go FS over 2 to the 20, I'll be at 9.53 hertz spacing in my analyzer. Is that making sense? Very simple calculations, though, nothing complicated. Truly, what I was always told, back of the envelope calculation. Now, do I carry envelopes around with me to write notes on? No. But I do have those scratch pads that I get in the mail for free from organizations that ask me for contributions, and they always include these little pads. So I have a stack of those pads, and my wife and I both use them. It's kind of like when I'm on the phone with somebody, I pull out one of those pads and I just write notes on it. Paper is still useful for a lot of little things like that. But at any rate, pretty straightforward building a spectrum analyzer. And the next sections, which we're not going to go through, just talk about the trade-offs of using a windowed spectrum capture, and then you'll have leakage effects and things of that sort that interfere. And then we get involved with the choice of the window to get the best resolution. We've seen Han and Hanning window in the past. So then that leads into what the windows look like when you transform them, but then eventually leads into a catalog here of properties of window functions. So I like the Han window, which here I called it Hanning, which is crude. His name is Han, but people called it Hanning's window, right? I went through that story before. But Ham is not the name of the individual. Hamming is a guy that developed coding theory. His name is Hamming. So, and Blackman is the name of a guy, and Bartlett is too. So it's probably true that Han got treated poorly. I think it's a Scandinavian name, if I'm not mistaken. At any rate, that window has side lobes that drop off at 18 dB per octave. Its main lobe is, these are some of the other parameters. These were some of the things that were used in your noise bandwidth calculations for the spectrum analyzer thing that you did on exam 2. That's where I got some of that information in that code that you used. I think I used the 1.5 in one of those equations. There's some other cool stuff in here. I just don't have time to go through it or ask about it, but they're interesting stuff. Scalloping loss, picket fence effect, dynamic range, and the fact that there's a signal buried down in here that's getting washed over by side lobe leakage. So I changed the window function to a Han window, and lo and behold, there is a signal there. If you were a fighter jet pilot and you were worried about somebody flying at you and you were looking for a Doppler shift off of a target out there, and your spectrum analysis looked like that because the signal was pretty weak, you would be sorely disappointed if there was a target out there and you missed it. You would like to be able to say, well, it's a fatter low, but at least I can see that signal out of the return. If it's a collision avoidance system, I don't know. Cars are going to get better collision avoidance systems, and they do processing of Doppler and things of that sort. Pretty much out of time now. So I'm going to jump over now to the project. I added in a bunch of hints. I added in one yesterday just to say that there's a minus sign that is actually in effect when you do problem 1, when you're doing the characteristic curve for the tracking loop. And then the rest of these things just help you formulate your code to track 4 signals at once. It's just sort of replication of what I've already done in CA track. You're just going to allow it to do 4 of them in parallel. And this received signal will come in, and I've given you how you construct that down here. I construct signals with codes 1, 5, 12, and 17, and I add noise onto the first one, and then I'm creating the others. I'm just not showing them all in here. Ultimately, though, I sum them all up, so this is the signal that goes into that tracking receiver. All 4 will be in there. You'll be able to use the correlators that are talked about in the original CA track, but it will now be able to pull out because you're passing in N gold, which N gold, you can see down here, has got a list of the 4 codes that you want to make sure you utilize when you despread. And if you do want that option, you want some hints for the optional problem, let's just see this thing updated. I put this in this morning because Kaylee was asking me about it. This just gives you some information on what the theoretical response is to the tracking loop. This is phase-lock loop theory, but it's control system theory, and COM1 actually has phase-lock loops in it, but not digital ones. So what I expect you to be able to do, and don't get worried about this. If you've got time and want to learn more, that's what it's really all about. This would be the way you would get the step response of the system. The closed loop system for the tracking loop looks like this system function, and then times the stimulus, which in this case would be a step, delta theta times u of n, and then phi there is the loop error. So you could formulate that up with some work into a difference equation model. You can use L filter in Python with the coefficients of the filter determined accordingly. You actually have to convolve through that delta theta over 1 minus e to the minus 1, so you have to do some more math on that. It'll become a third order denominator. And then how do you choose K1 and K2? You'd focus in on, I can't write on this, but you'd focus in on K1 is the right-hand side there in terms of damping zeta and natural frequency omega n, which would be radians per second. And Fs is the sampling rate, which you can just assume to be the 1 millisecond, because you're updating every millisecond. So that's 1 kilohertz, right? Fs is 1 kilohertz. I think the loop damping is 0.707, and the bandwidth, I think, is 100 hertz. Is that right? Does that sound right? It's 10 less than the sampling rate, so it's pretty good. How do you get this? These equations here can be utilized by using the noise bandwidth to solve for omega n given zeta. So in most COM systems, we specify the loop bandwidth in hertz. Control systems people like radians per second, but comms people like me like noise equivalent bandwidth Bn, something you learn about in COM2, and damping factor. So, and those are just the definitions of the terms. Don't feel bad. She asked, and I'm going to give a hint, so I'm going to give it to everybody. It should not be high on your priority list. I know you're multitasking right now over a lot of different tasks. I am too. I'm not going out in the style of some politician that just got fat on some money and didn't have to do anything. I mean, there's things in the news all the time about stuff. Trump was in the news yesterday, right? All the fines that are going to be levied against his company. But that stuff happens all over, so don't think that. I'm sure he's going to be saying in the news pretty soon that everybody does it. Well, is that the standards that you live by? No. At any rate, now I got about 5 minutes to talk about the review. So I'm going to try to take some notes on here, and you can take notes on your paper copy. It is comprehensive. New material that you haven't been tested on will be emphasized. I'm not going to give out any sample exams, but I am describing things in here. It's going to be about 5 pages. The exam is on Wednesday. I looked on the exam schedule yesterday. This room, 8 to 10. That's our time. I'm going to try to be here at 7:30. You can get comfortable if you need your drinks and anything else, except your cell phone. You can't use that in the exam. Can't use your laptop. But you can bring in your textbook, and if you've made paper copies of the notes, you can have those. I'm not going to let you go online because that's just not practical. I might have a binder up in my office that has notes that somebody gave me after last fall's exams. I don't know. If I find it, I will let you know. I'm not going to run them off, but last year somebody in the class volunteered to have a binder that could be shared during the exam. The first priority, though, should be to have a crib sheet that you could write of high points, because it just helps you study, right? That's how you study. And then go to something like that if you need to. It turns into a noisy place, so if everybody's wildly leafing through pages, I just have seen it. To me, it's an interesting psychological study. It will be quiet, and then all of a sudden, but hopefully everybody will feel comfortable with that, because that's brains working, right? If you go take it at the testing center, I always feel like you're at a disadvantage because you're sitting there by yourself. Does anybody have a comment on that? I'm just curious, over all your years, have you ever had to take it at the testing center by yourself? I always feel like it's like in a vacuum. And in a vacuum, it's like time stands still, and your ability to think can actually, I feel like, can be diminished. Whereas if you know other people are working, it kind of makes you feel like you need to be working too. So 5 pages is nominal. If I need to give you more writing space, I'll maybe add a 6th page. So what are some relevant topics and not relevant topics? First bullet there, discrete time signals and systems in the time domain and frequency domain. It's pretty basic. It's pervasive. It's for sure possibly a convolution, some. I just said likely. If I was to ask you right now, do you want me to put no on that, not likely? I could downgrade it. I could say not too likely. I can't say no, because that's too limiting for me. I don't know what I've got picked out right now. This one, though, the classical solution of LCCDEs, that's a goner. That won't be on the exam. You will have things with DTFT, just like we've been talking about. That's from chapter 2. That's sort of inherent, and transform theorems to work something. So that's, got to be there. Z-transform, I for sure have a problem on that. And that's like a fun problem, right? It'll be something with partial fraction, just using the tables. Does anybody not want to have a problem like that? It'll be worth maybe 15 to 20 points. I mean, that should be like bread and butter. That I absolutely have a problem like that picked out, so for sure have that. Low-pass sampling theory, I mentioned how it could show up in an FFT problem. Spectrum analyzer, just have to think, got a sample at greater than twice the highest frequency. It'll weave its way in somehow. It's not a big deal though. Multi-rate sampling and upsampling, I say almost certain because I consider it to be fundamental, and I haven't seen the class universally work those very well. I've had a lot of issues, so I'm going to give you another go at it. It will be a page that has a block diagram, and it will say, draw me the picture here, here, and here. And if I say I want you to plot from minus 2 pi to plus 2 pi on each one of those, I want it. I want it that way, because that helps you visualize and helps me see if you made a mistake here, oh, that's why this one's messed up, and so on. Just do it. So, got that. Quantization, noise, possible, but nothing extensive. It might just simply be, I feel like I need some water. I guess I could pull my microphone out and destroy it here too, but I don't want to do that. It might just be, a simple calculation for signal power. Sinusoid, it was always a squared over 2, and then the quantization noise power. Amazingly, a lot of people had problems with that. I don't know, it's not, I say possible, it's not a guarantee by any means. Transform analysis, which was chapter 5, definitely. There's some nice problems. There'll be pole zero plots. There'll be, these two are kind of coupled together. Actually, these three are coupled together. They're all from chapter 5. All pass, minimum phase type of thing. I mean, one of the problems, there'll definitely be a problem on that. And one of the things I like to do that's easy but not detailed and messy for me to grade is just say, here's a system, pole zero plot, draw 2 pole zero plots like you did on exam 2, where you just said, here's the minimum phase, here's the all pass system, here's the minimum phase, and the linear phase. I mean, I can do that in a variety of ways. But you won't have to actually write out the polynomials. You'll just have to be able to draw the picture. Hopefully that sounds cool. Structures that we just did, not a whole lot I can do with that, but it'll be tedious if I, depending upon how I do it, I can have you, give you a ratio of polynomials and say, draw a particular type of structure, direct form 1, 2, cascade, probably not parallel. Or I can give you the flow graph and have you have to figure out what h of z is. I'm more likely to do that, and that's the more challenging problem, I think, because you have to actually write the equations down, flip to the z domain, and then try to write that ratio out. I'll just tell you right now, that's kind of what I'm going to very likely to do. There's going to be a problem in that for sure. It's just what type it will be. It's either one way or the other way. I've got to study some more of my old exams still. Nothing on FIR in particular, because there's nothing too really exciting about that. Finite precision, really, the most I can do would be a shorter answer or concept. The only problem you really worked in finite precision is due on the homework from last week, where you're changing the quantization level. So just understand that with quantization, some undesirable things could happen. And in that particular homework problem, remember, it's the stop band that starts to get some extraneous things. I never ran that. They're going to be killing me right now, but there's an example down here at the end, which I never ran, at the very end of this, where I did the pole zero plot of this quantized thing. And yeah, this picture right here, I'm not going to try to run it right now, but rather than the poles showing up on the unit circle, they will kind of be broken apart. And they will be like quadruplets, but they won't be in the unit circle anymore, so there'll be 2 in and 2 out. One of the things I want you to think about is if you quantize a polynomial or coefficients that are symmetrical, you quantize them all the same, the left and the right end will get the same quantization. So does that maintain symmetry? Does, right? So that means when you root that polynomial or build the filter, it will be linear phase. So quantization does not destroy the phase linearity when done in that fashion. So this picture would make that clear to you, but no time on that. Some simple FFT applications. Circular shift time is about all I can do. I'm going to try to avoid doing a circular convolution. More likely it would be circular shift, because these are tedious problems to do. But then a general systems level view of FFT, IFFT, and this picture down here is kind of what we went through already with the spectrum analyzer idea. Delta F is Fs over N, and when you get the spectrum, these are some of the symmetry properties that you need to know that are present as well. And I'm way past. I don't know why she's not in here yet, but they're out in the hallway though. So I'm going to go up to the lab and I'll take questions. If your quiz is right away, I'm not going to interfere with that. So let me stop this.